Alright, so today we're going to talk about a different method of doing some integration, and it's called integration by substitution and separable differential equations. And what this is a way that we can actually break it down and make our integration, or some of the integration problems we're going to look at, make them into simpler ones that are very easy to recognize what the antiderivative is. That is, if you know your derivative rules. If you don't know your derivative rules, you still need to go back and look at those. Make sure you memorize those, and because this entire chapter, all we're doing is doing derivatives in reverse. So if you don't know how to do them in the front way, you're definitely not going to know how to do them in reverse. So go back and look at those. Make sure you know them. It'll make things so much easier. Now, the chain rule allows us to differentiate a wide variety of functions, but we are able to find antiderivatives for only a limited range of functions. There are going to be a lot of functions that you're going to run into that you're going to try to take the antiderivative of or the integral of, and you can't do it. And that's one of the reasons why, like in the last section of the last chapter, we talked about approximations. That's a case. We're going to look at other ways of approximating it as well as we get further into calculus. Specifically, if you're in BC, you're going to look at a way later. AB won't get there, but it's called Taylor polynomials and Maclaurin polynomials, and that's a way that you can use derivatives to actually come up with a polynomial approximation for a function. But anyway, but there are situations where we can sometimes use substitution to rewrite functions in a form that we can integrate. So what we're looking at today with our use substitution is this is essentially going to be the power rule of your anti-differentiation. That's what we're looking at. All right, so for instance, let's look at this right here. And what we're going to do is we're going to let u equal x plus 2. Now, if we let u equal x plus 2, we're going to have to also find out what du is. So we're going to find out that du, just take the derivative of this, and that's going to be 1. So you get 1 dx. What we actually did here is we took du dx and then multiplied both sides by dx. But anyway, we're moving the dx to the other side. So now, if du equals dx, that means we can put du anywhere we have a dx. And just like in the same way, we can put u anywhere we have x plus 2. So we have u to the 5th times du. So now we have the integral of u to the 5th du. And of course, then all we have now, you've got this a lot simpler. It's just a reverse use of the power rule. So we're going to increase that power by 1 and divide by that same number. So we end up with 1/6 u to the 6th plus c. Now, the variable of integration must match the variable that we're in the expression. That's what we have here. And then once you get to this point, now you can go back and you can plug back in what u was into your expression to make it exactly like it should be. So you're going to end up with 1/6 x plus 2 to the 6th power plus c. And that's just another way of writing it. Dividing by 6 is the same thing as multiplying by 1/6. So don't forget that. And you always, if you use substitution, do not forget to substitute the value for u back into the problem. Don't leave it in terms of u. All right, so here's another one that we're going to look at, and let's work this one out. We know that, let's go ahead and say we're going to let u equal 1 plus x squared. That means that du, if I take the derivative of this, I'm going to end up with 2x dx. All right, so now right here I've got 2x dx. So if 2x dx equals du, that's going to become my du. And then over here, I've got the square root of 1 plus x squared. Well, 1 plus x squared is just u, so this is the square root of u. Now, in the same way we dealt with the derivatives of square roots, we can also deal with the integrals of square roots. So what you can do here is you can actually rewrite that as u to the 1/2 du. So now all we have to do is do the power rule, which means we're going to increase this by 1. So it's going to be 3/2. And then I have to divide by the reciprocal of that. Sorry, I have to divide by that number, which is divided by 3/2 is the same as multiplying by the reciprocal, which is 2/3. So I get 2/3 u to the 3/2 plus c. And then I can go back and I can plug back in my u. So you're going to have 2/3 1 plus x squared to the 3/2 plus c. See, not that big a deal. Now, another way that you can do this here is you can always solve for your dx, and you can plug that in right there. This is just another way, and if they don't match up exactly the same, like this one matched up exactly right here. So that's a good thing. We can recognize that we're going to put du in here. They're not always going to match up exactly. So sometimes you can get by multiplying or solving to the point where you leave dx on one side all by itself, so you solve for dx. Then you're going to put this thing right here in there in place of dx. So you'd end up with 2x du divided by 2x. And of course the 2x's would cancel out. Let's say this had been 5x dx, and you solve this and you plug it in there, and you'd end up with 5/2 du at the end. It just makes it easier to do it this way sometimes when they're not going to cancel out exactly. All right, notice that this only worked because of the 2x in the original. Many integrals cannot be done by substitution. If you don't have this 2x right here, then there are some value of x right there. You can't actually do this. So be careful. Don't force something that actually doesn't work. All right, so let's work on this one right here. We've got the integral of the square root of 4x minus 1. Typically what you want to do is you want to let u equal the function inside of the function, the inside thing. So for instance here we're going to let u equal 4x minus 1. And when we find du, we're going to end up with 4 dx. Take the derivative of that. It's 4 times dx. Now, notice I only have dx here. So what you can do, solve for dx, which means I'm going to divide both sides by 4 or multiply both sides by 1/4. So 1/4 du equals dx. So in place of this dx right here, I'm going to put 1/4 du. So this becomes the integral of the square root of 4x minus 1, which is u. Square root of that I can rewrite as u to the 1/2. And then I've got the dx, which is 1/4 du. Now, what can I do with that 1/4? Well, it's a constant multiple, so I can move it all the way out front. So it's just going to tag along, and then I've got u to the 1/2 du. Remember, these have to match, the variable here and the variable there at the end with the d. So now we have 1/4. It's just tagging along. And what's the antiderivative of u to the 1/2? Well, we just did that. And it was 2/3 u to the 3/2 plus c. So now we're going to have to multiply over here. And technically, you're actually multiplying times all this. But what's 1/4 of some random constant c? It's just some new random constant c. So we don't have to worry about it. The c is really easy to deal with until you actually solve it. Don't do anything with c unless you have to. But 1/4 times c is just 1/4 c or some new c. So don't worry about that. So all you're worried about multiplying is this part right here. So you get 1/4 times 2/3, and that's going to give you, the 2's are going to cancel here and here, gives you 1/6. Yeah, 1/6 u to the 3/2 plus c. And then of course you can plug in your u. So you get 1/6 4x minus 1 to the 3/2 plus c. And there's your answer. All right, for example 3, once again, we're looking at something inside of another thing, and that's where we typically are going to want to use the u substitution. So we've got the cosine of 7x plus 5, and we're taking the integral of that. So u in this case is going to equal 7x plus 5, and that makes du equal to 7 dx. All right, now once again, we only have dx here, so let's go ahead and solve for dx. We're going to divide both sides by 7. So we end up with 1/7 du equals dx. All right, so when we substitute and put everything in, we've got our integral of cosine u, and then in place of dx, we're going to have 1/7 du. Now, once again, we can move that 1/7 all the way out front, and we have cosine u du. Now, what is the antiderivative of cosine u du? Well, that's just going to be sine, so we end up with 1/7 sine u plus c. Then we can plug in what our u value is, and we get 1/7 the sine of 7x plus 5 plus c. Now, remember guys, on all these antiderivatives, you can always go back and check. If you were to go and take the derivative of this thing right here, the derivative of 1/7 sine 7x plus 5, well, derivative, you're going to have 1/7 just to check it. Now this red is just checking it. I'm taking the derivative. Remember, with the constant multiple out there, you're just going to tag along. What's the derivative of sine 7x plus 5? Well, you're going to be, derivative of sine blob is going to be cosine blob, and then times the derivative of the blob, which is going to be 7. Well, what happens with the 7 and the 1/7? They're going to cancel each other out. And what about the derivative of the plus c? Any constant as a derivative of 0. So you get the exact same thing here that you started off with here. You can always go back and double check your work by taking the derivative of what your answer is. It should equal the same thing that you started off with. If it doesn't, you've done something wrong. All right, so this one, let's do it. And once again, we're going to look for what's inside of another function. And we've got x cubed here is inside of the sine function. So that's probably going to be a good choice for us to try with u. Now guys, I'm going to go ahead and tell you, you may make some decisions that are not the greatest at the first, but you typically want to look for what function is inside of another function. That's going to be your first clue for u substitution, but you may choose the wrong one. It's okay to make decisions and make the wrong ones. Just go back and fix it. Go back, if it doesn't work out, go back and try something else. So here, I'm going to let u equal x cubed. And one of the clues here that you want to see, if I take the derivative of x cubed, am I going to end up with some constant multiple of this thing right here? Because that is going to have to be taken out with a dx, right? To change those things over. So that's what you're looking for. So when I take the derivative of this, I'm going to get du is equal to 3x squared dx. So while it doesn't match exactly with x squared dx, I can always divide both sides by 3 and get 1/3 du equals x squared dx. Now you could also move the x squared over and solve for dx and plug it in. Your x squared is going to cancel out anyway. I just like to do this. If I know what I'm solving for, like the x squared dx here, I solve for it. So now I know this is a direct substitution for that. That is going in place of the x squared dx. So now I'm going to get rid of the x squared dx, and the sign of x cubed is sine u. So I end up with the sine of u, and then in place of x squared dx, this whole thing here, I'm going to put 1/3 du. And of course the 1/3 can move all the way out front. So you end up with 1/3 times the integral of sine u du. And the antiderivative of sine u is negative cosine. Remember, you're going backwards. Don't forget your rules. Sine, cosine, negative sine x, negative cosine x. And in this direction, we're going dy dx. We're taking the derivatives. So if we want to do the opposite, we go backwards. So the antiderivative of sine x, we would follow the arrow back to negative cosine x. We get negative 1/3 cosine x, cosine u plus c. Then, of course, we can plug in our u, and we get negative 1/3 cosine x cubed plus c. And that's pretty much all there is to u substitution. There's not really a lot to it. And see, here's the situation like I told you where you could solve for dx. And here, notice that they moved the x squared to the end, and the x squared is going to cancel out. You're still going to end up with 1/3 the integral of sine u du. So just two different ways of looking at it. Doesn't matter which way you do it. They're both correct. They're both just algebraic versions of each other. All right, so this one's kind of a trick question, but once you know how to deal with it, it's actually really easy to see and really easy to solve. But you're going to have to rewrite this thing first. Now, some of you probably look at this and you say, oh, well, I can recognize exactly what that is right now. But a lot of you are going to miss this unless you rewrite it. Remember what sine to the fourth x is. That is just another way of saying sine x to the fourth power. So in this case, now once we get it in this form, it makes it a lot easier to notice what we're going to do for our u. So u is going to be sine x, and du would be the derivative of sine x, which is cosine x times dx. and we just happen to have cosine x dx right there. So now when we do all of our substitution, in place of sine x, we're putting u. We have u to the fourth. And in place of cosine x dx, I'm going to put du. All right, and then once you get there, it's just a power rule problem. So you're going to increase that by 1, divide by the same thing. You end up with 1/5 u to the fifth plus c. Plug in your u, you get 1/5 sine to the fifth x plus c. And guys, you could also have left that as sine x to the fifth power. Either one of those is perfectly okay. They are two ways of writing the exact same thing. Just remember, the only reason why you don't do sine x to the fifth and they move the 5 in here is because that could be, if you don't have the parentheses, that means you're doing the sine of x to the fifth. That's the sine of x to the fifth. So you're doing the x to the fifth first, then taking the sine of it. But if you do this, you're taking the sine of x first and then raising it to the fifth power. But that's why they move it in here, is to signify what that thing is, sine x raised to the fifth power. Don't make those mistakes and get those mixed up. All right, so this one's a little different also in the fact that, well, looky here, we actually have upper and lower bounds. And there's a little bit of a trick to it, but not too bad. But let's look at the antiderivative first, and then we'll talk about the bounds. Let's just kind of leave the bounds off for now. So one or two things you can do here. And either one of them work. And I'm going to show you that both of them work. You can use tangent as your u. And I know some of you are thinking right now, well, wait a minute, on that last one you just said secant squared, or secant x squared, so secant would be, hold that thought, we'll talk about that in a second also. But we can let u equal tangent x. And the reason I think that and I see that is because what's the derivative of tangent x? Well, it happens to be secant squared x. So that means that du dx, or du, is going to be secant squared x dx, which I happen to have, boom, right there. So that way works in the same way that we could also, and this is the other one, let me go ahead and show you it. I'm not going to work them both all the way out, but you can go back and work them out if you want to. Let's say I let u equal secant x. Well, it's still going to work because what's the derivative of secant x? Well, it's secant x tangent x. So we end up with du equaling secant x tangent x dx. So if we split this up, let's say we bring one of the secant x's, actually let's bring both of the secant x's to the front, but I'm going to write them separately. Secant x times secant x, that's secant x squared, correct? And then I still have my tangent x, and then I have my dx. So u is secant x, this one, and then du is secant x tangent x dx, which is all of that right there. So either way, what do we end up with? We end up with u du. All right, so let's do this. I'm going to do it with the purple. I'll leave that up there so you can actually see that if you want to go back and check that one. But I'm going to do it with the purple here. So we know that tangent x is going to be u. We got the integral of u, and secant x squared dx, or secant squared x dx, is going to be du. All right, now right here is where we have to stop and think. When we talk about this upper and lower bound here, what variable is 0 and pi over 4 based off of? Well, the thing is, they're based off of this variable right here because that's what you're integrating with respect to. So 0 and pi over 4 are given to us in terms of x. We can't write 0 and pi over 4 here because this is now an integral in terms of u. Now, there's one of two ways you can solve this. You can go ahead and you can swap these over into terms of u. The way you do that is, well, your u substitution. For instance, right here. You know that u equals tangent x. So if I wanted to find what u was at 0, you're going to end up with tangent of 0. All you're going to do is you're going to take this value right here and plug it in right there. So what is the tangent of 0? Well, remember, tangent is sine over cosine. And when we're talking about 0, sine of 0 is 0, cosine of 0 is 1, so we end up with 0. So our lower bound is still going to be 0. It's not always going to be the same thing. All right, and if we do u at pi over 4, that's going to be the tangent of pi over 4, which is the sine of pi over 4 over the cosine of pi over 4. And what do we know about sine of pi over 4 and cosine of pi over 4? Well, they're the same thing. Remember, sine and cosine have the same value at pi over 4, so we end up with the square root of 2 over the square root of 2. We end up with the square root of 2 over 2 divided by the square root of 2 over 2. Well, anything divided by itself is just 1. So we're integrating from 0 to 1 u du. So when you integrate that, you're going to have u to the first power. You're going to raise that to the second power, so you're going to end up with 1/2 u squared. Now remember, with a definite integral, we talked about this in the first section, you don't need the plus c. So we're now going to integrate this thing and evaluate it from 0 to 1. So you're going to plug in the 1. So you end up with 1 squared, which is 1, times 1/2. So you end up with 1/2. And then minus, plugging in the bottom, 0 squared is 0. So you end up with 1/2. So there is your answer right there. All right, now let's say we did not want to find the upper and lower bound here. Let's do this just a little bit differently. I'm going to skip from here to there. Actually, I'm going to skip from the beginning down to here. Not even going to get to this part. So we're going to get the integral of u to the first du. I'm going to go ahead and evaluate it. So my integral, that is. So I'm going to take the antiderivative of u to the first du. You're going to get 1/2 u squared plus c. Now you're going to plug in your tangent back in place of u. So you end up with 1/2 tangent squared theta, x, sorry. Now, instead of the plus c, I'm going to go ahead and go back into the whole developing and actually integrating, evaluating it from the upper and lower bounds. Now, since I'm in terms of x here, I'm going to start from 0 and pi over 4. Because remember, those are the ones based on x. So now, what happens here when we do this? Well, now we're going to plug in pi over 4. We're going to get 1/2 the tangent of pi over 4. Let me go ahead and squared. I'm going to write it a little different. Minus 1/2 the tangent of 0 squared. So the tangent of pi over 4, once again, is 1, like we found up here. And we have 1 squared, which is 1, times 1/2 gives us 1/2. And then the tangent of 0, which we found up here, is 0. 0 squared is 0. 0 times negative 1/2 is 0. So we end up with 1/2 again. Two different ways of doing the exact same thing, with whatever you got. Now, one thing, let's go ahead and go back and all right, so here's the one where we actually find the new bounds with based on u. It's not that much difference in the amount of work. You're going to have to evaluate them at these values anyway, whether you plug it back in or whatever. So it's about the same amount of work either way. Now, here's the thing I do want to point out. Right here, 0 to pi over 4 of u du. You will notice that when I was working that out, I made a conscious effort not to write that down. You cannot write this down on anything where you're having to show work and they're grading your work, because the limits here do not match the variable you're dealing with. Remember, 0 and pi over 4 are in terms of x. The 0 and the 1 were in terms of the u. So right here, this would cause you to lose points. Now what you can do is, like I did the second time, leave those limits out until you substitute back in. And you don't even have to really put the plus c, since you're not going to use it anyway. All right, so I want you guys to try this one. I'm going to pause the video and work it out, and I want you guys to pause the video and work it out and give it a try, and then come back and check your work. All right, so here's the work. I'm letting u equal x cubed plus 1. That looks like it's going to be the best way to do this, because it's inside of the square root, and if I take the derivative of x cubed, I'm going to get 3x squared, so it works out. So u equals x cubed plus 1, du equals 3x squared dx, which I have, boom, right here. So then when I do my substitution in, u goes in place of the x cubed plus 1, and du goes in place of the 3x squared times dx. Now, I went ahead and found my bounds in terms of u, and all I did was plug these values right here in right here. So when I had the u at -1, I had -1 cubed plus 1. Negative 1 cubed is -1. -1 plus 1 gives us 0. When I plug in 1, I get 1 cubed plus 1, which is going to give me 2. So we're integrating from 0 to 2. So I rewrote that as my u to the 1/2 power, and then took the antiderivative of it using the power rule. So we end up with 2/3 u to the 2/3 power, or 3/2 power, sorry, evaluated from 0 to 2. So then I plugged in 2, and I plugged in 0, and I subtracted them. Plug in 2 first, upper bound, and then subtract when you plug in the lower bound. So we end up with 2/3 2 to the 3/2 power minus 2/3 0 to the 3/2 power. Now, of course, that's going to be 0, so that's not going to be a big deal. Over here, there's a couple ways you can go about this. You can take the square root first. If you take the square root of 2 first, you get the square root of 2. Multiplying that, or raising that to the 3rd power, you end up with square root of 2 times the square root of 2 times the square root of 2. And those first two square roots of 2 would give you 2. Or you can raise 2 to the 3rd power and get 8, and then take the square root of that, which simplifies down to 2 square roots of 2. Either way, you're going to get 2/3 times 2 square roots of 2 minus the 0 from this one, and then when you multiply that out, you're going to end up with 2 times 2 gives you 4 square roots of 2 over 3. So there's your answer. All right, the next topic we're going to look at is called separable differential equations. And we talked a little bit about this. A differential equation is just an equation that has a derivative in it. And then you're going to end up solving to, you're actually working backwards to solve for y. So a separable differential equation can be expressed as the product of a function of x and a function of y. This is just the separable type. There are many different types of differential equations to the point that there is a class that is specifically on just differential equations. But a separable one is an easy one to deal with, and that's the one that we're going to deal with. And it has a function of x and a function of y on one side and dy dx on the other. And what you're going to do is you're going to end up getting the y function over here with the dy, and you're going to multiply both sides by dx and get the dx over here with the x function. So for instance, we have dy dx is equal to 2xy squared. So what you want to do here, you're going to multiply both sides by dx and divide both sides by y squared to separate the variables, and we're going to make the assumption that y squared is never 0, so it doesn't go undefined. So we get this situation right here, and then we're going to rewrite that so that we have y to the negative 2 dy equals 2x dx. Now, hopefully this kind of looks a little familiar, and it kind of setting your spidey sense off here. It should, because then all we're going to do is we're going to go in and we're going to integrate both sides. So when we integrate both sides, it's going to get rid of the dy and it's going to get rid of the dx so that we can actually solve this. All right, so over here, increase that and divide by that number. So we end up with negative y to the negative 1 plus some value c1, a constant, for that side. And then on this side, the antiderivative of 2x dx is going to be x squared plus c. That's another constant from this integration. But what we're going to do is we're just going to combine those and make one big c. I'm going to go ahead and move that one over. Doesn't matter whether it's positive, negative, whatever. We can move those over so we have one c altogether. So we're going to end up with negative 1 over y is equal to x squared plus some big C. So we've just taken these two common, the constants of integration, combined them together. All right, now we want to solve for y, not negative 1 over y. When we're solving these, we're looking to solve for y. So right here, we're going to, first thing we're going to do is we're going to multiply both sides by a negative. Actually, let me back up just a touch there because I want to work this out so you guys can follow what's going on here. All right, so first thing I'm going to do is I'm going to multiply both sides by a negative. So you end up with 1 over y is equal to negative x squared plus c. Doesn't matter if it's a plus or minus. That's going to work out only when you solve for c. So you can put minus c, but it's not that big a deal. All right, and then at this point, what I want to do is I want to go ahead and think about this as being over 1. The reason I can do that is because if I know that 1 is to 2 as 3 is to 6, guess what I also know? I also know that 2 is to 1 as 6 is to 3. So if I have a ratio here, or a if I have a situation where I have two ratios are equal to each other, I can flip them over. So if I flip 1 over y over, I'm going to end up with y. And over here with this one, I'm going to end up with, and I can just factor this negative out, bring it out front. It's going to be 1 over x squared plus c. So see, they're not real difficult. But I will go ahead and tell you that there is usually one of two things on the AP exam, and we've talked about this already. There's usually either a separable differential equation or there's one of those big ugly things that we've already dealt with back in derivatives, one or the other. And it's usually the major part of one of the free response questions. I mean, up to being 5 points. So you really need to know how to do these. Not to mention, if you're going into any kind of technical field, you're going to have a differential equation class anyway, so you definitely need to know how to do them. All right, so let's look at this one. So what we're going to do is we're going to leave the 2x e to the x squared on one side, and we're going to move the 1 plus y squared over to the other side by dividing. We're going to multiply both sides by dx. So what you end up with is 1 over 1 plus y squared dy is equal to 2x e to the x squared dx. All right, and once again, then we can integrate. And over here, we're going to actually have to use u substitution, where u is equal to x squared, and du is going to equal 2x dx. So the 2x and the dx go away, so we end up with what right here? If we do our substitution, let me write that below it. So if we write this below here, the 2x dx goes away, so that and that becomes the du. And e to the x squared becomes e to the u. So that is nothing more than e to the u, which is e to the x squared plus c. So this side over here is e to the x squared plus c. The plus c is not in the power. It's afterwards. And then over here, this one you're going to have to recognize something here. It's 1 over 1 plus y squared. Well, you may be more familiar with this as 1 over 1 plus x squared, which is going to be the derivative of the inverse tangent. Now, this plus c over here, don't forget, that's the combined constants from both sides. So I've got the tangent, the inverse tangent of y equals e to the x squared plus c. Now, once again, what do we know? We want to solve for y. We don't want to solve for the arctangent of y. So what we're going to do here to deal with that situation is we're going to undo the inverse tangent by taking the tangent of both sides. So here, if we take the tangent of the inverse tangent of y, we're going to end up with just plain old y. They cancel each other out. And if we take the tangent of e to the x squared plus c, well, we've got the tangent of e to the x squared plus c. That e to the x squared plus c has to be in parentheses because that plus c is attached to the e to the x squared, not attached after we've taken the tangent. Now, this is called an implicit function of x. Implicit simply means that there is a function, there's an x in there somewhere, but it's not solved for y or x specifically. We can find y as an explicit function of x by taking the tangent of both sides. When you do and you solve like we just finished up doing, solving for y, that's solving explicitly for y. All right, and once again, notice we cannot factor out the constant c because the distributive property does not work with tangent. We're taking the tangent of this whole thing, not the tangent of this and the tangent of that and then add them together. That's not right. All right, I want you guys to try these, and I'm going to show you what the answers are. And if you have any questions, we'll actually talk about them in class. So read this, give it a try, pause the video before you look at the answer and give it a try. But you should come up with this is a false statement. And you should be able to tell me why. All right, the next one, read the question, give it a look over, we'll try to work it out. Pause the video, give it a work it out, and then see if you can come up with the right answer. Okay, the right answer is true. This actually is true. You have to use some of your rules for logarithms there, properties of logarithms. All right, next answer. And I'll give you a hint on this one. You want to use the definition of what tangent is. Tangent is sine x over cosine x. Use that and see what you can come up with some u substitution. All right, pause the video, give it a try. All right, the correct answer for this one is D. All right, a definite integral that you're going to want to, well, dang it, that you're going to want to work out. I'll show you the answer since I've already done it anyway. But you do want to make sure that you know how to work this out. Remember, we're doing an antiderivative. So where you were taking the derivative of e to the 2x before, remember you would multiply by the derivative of the 2x. Here you're going to divide by the derivative of that 2x. So you end up with 1/2 e to the 2x. Then you plug in the 2 and you subtract when you plug in the 0. So give that a try, verify you can get that answer. All right, this is kind of using some of the properties and everything and your knowledge of the properties of integration. Pause it. Try it out, see what you can come up with. Happens to be the exact same thing that it was before. If you don't understand that, ask tomorrow in class and we'll look at it. All right, if the differential equation dy dx equals f of x leads to the slope field shown below, which of the following could be the integral of f of x dx? All right, so this is one of those situations where you're going to want to find out which one of your trig functions it's going to be. Well, I mean, looking at this thing, you can see an up and down movement, so you can see it going through the motions of the waves. But can you tell me why it's A? I know I've already shown you that it was A. Can you tell me why it's A? That's the big thing. Now you could break it down and you could get some points here and there and all over the place, but more specifically, if you're looking for the behavior, remember the plus C part is nothing more than a vertical shift. All right, that's all of 6.2.